You're listening to the FQxI Podcast. Today,
which would revolutionize everything. The thing, of course, is that I haven't seen anything about this since then.
we begin counting down the biggest stories in physics of 2023.
I don't think we're anywhere near the realm of, the robots are going to take over and humanity is doomed. We had a campus-wide emergency meeting called as a result, and a lot of colleges and universities did the same thing.
With quantum physicist Ian Durham.
Now, that doesn't mean that Earth and Earth's atmosphere actually is a quantum state of matter. It's not.
I'm Zia Morali. Welcome to the podcast from the Foundational Questions Institute. Gosh, here we are again at the end of another year. And I'm joined, as always, during this festive season by quantum physicist and FQxI member Ian Durham of St. Aronson College in New Hampshire. Hello, Ian.
Hello, how are you?
I'm good. I'm very excited, I have to say, about number one. I won't say any more about it other than I was a bit surprised, but it's just lovely. It just feels very FQxI.
It does.
So please stay tuned. It's a good one this year. For now, we're counting down the top 5 biggest advances in foundational physics. And here I emphasise it's meant to be the top 5 because somehow, Ian, I seem to be looking at a list of about 15 different stories, once again, that have snuck in as runners-up and joint winners. I think FQxI needs to get you under control. But anyway, let's start off with what hasn't made the top 5 for, reasons good or bad.
So the first is that there were 2 competing claims this year about room temperature superconductors.
So we're talking about 2 different things here. The first is a series of papers by University of Rochester physicist Rangadias and co-authors. One paper published in Nature in March of this year said that his team had discovered that a compound of lutetium, nitrogen and hydrogen could superconduct at room temperature and moderate pressures. But that was later retracted in September this year. That follows the retraction of 2 other papers in Physical Review Letters and Nature, going back to publications in 2022. And the other claim you may have seen went viral over social media from South Korea was that a lead-based compound LK99 is a superconductor at room temperature and ambient pressure, opening up, and I quote, a new era for humankind. So, clear candidates for number 1 on our list. What happened, Ian?
So the first referred to this LUNH as lutetium, nitrogen, and hydrogen. There was a claim that it superconducted at a temperature up to 294 Kelvin when it was sort of squeezed to a relatively moderate pressure of 10,000 atmospheres, which is not really that reasonable if you're a human being, but nevertheless is reasonable. And there was supposedly a claim by a guy at the University of Illinois Chicago that he had replicated this work. Nevertheless, these papers have been withdrawn after a number of the co-authors argued that it should have been withdrawn. And then sometime in the summer, I believe it was, there were a couple of papers uploaded to the archive preprint server by this group in South Korea that claims that this stuff called LK99, which is a lead-based compound, not only was in room temperature superconductor, but this is supposedly ambient pressure, which would revolutionize everything. The thing, of course, is that I haven't seen anything about this since then. There were apparently debates among Korean researchers about whether that research ever should have been released to begin with, especially considering they had known at that time that the guy from the U of R had retracted the papers about his claim. So they knew that it was a really controversial thing to publish. There's been a bit of a rush to publish in a couple of cases, and there's a whole sociological question there about why.
So that's what I wanted to ask you a little bit about. I don't think we want to dwell too much on the whole room temperature superconductivity and all of the excitement about that. We seem to talk about it every year and how groundbreaking it would be if it was done. And on the podcast page, qspace.fqxi.org/podcast, I will put links to various articles about both of these pieces of work. A very interesting one from Science, which has got all sorts of backstory and gossipy stuff about, the authors who tried to have that paper retracted from Nature, and how the lead author sent out like a cease and desist letter to them. There's all sorts of intrigue going on there. We're not best placed, I think, to speculate on exactly what has happened. But what I wanted to ask you about is the sociological issue and a question about the value of publishing. And it's because we've got these two controversial things that happened. One of them, as you say, the LK99. This one wasn't even published in a journal. It's gone out as a preprint, and then I think there was a video that went viral. For a while, everyone was talking about it. Well, not everyone, but everyone who was interested in physics and that sort of thing was talking about it. At the same time, people were very, very, very skeptical on social media about it. And then it was a big flash in the pan and it disappeared. It couldn't be replicated. Whatever happened, we don't even know. That's sort of an example of how people can get very excited about something. It's just gone out as a preprint. It hasn't been peer reviewed. And then we've got this incident with multiple papers that were peer reviewed from the University of Rochester. They were peer reviewed in very prestigious journals. And then there were questions about the kind of analysis of the data that had been done and how it had been treated in order to understand exactly what had happened and whether the process that was used there was correct. I guess what I'm getting at, and bearing in mind that we have a very mixed audience, so we have an audience of people who are professional scientists who go through this process a lot, and we have an audience of people who, this isn't their day job. They don't necessarily understand the whole peer review and journal process and publishing process in science. What is the point of journals and peer review? How does this process work, and how do we reach a point where there can be a lot of excitement about something that hasn't even gone into a journal, and there can be excitement about something that's gone into a journal, but we can't necessarily assume that that means that the work can be replicated?
These are all very interesting questions. Modern science is built on this idea of peer review, but peer review in the way it is practiced now is a relatively newish kind of thing. The concept of a journal is relatively old. The first two journals in science were, I believe, the Philosophical Transactions of the Royal Society, and there's a comparable one for the French. I can't remember, the French Academy of Sciences or something like that. And those date back to like the 1600s. But for a long, long time, papers were published in these journals. Someone involved sponsored them. So in the Royal Society, if you were a member of the Royal Society, you could sponsor someone's paper in the journal. But the way modern science now works, though, is the idea is that you send off a paper to a journal, and a series of referees who are presumably your peers, people with knowledge of the field, read your paper, decide whether it merits publication or perhaps, as in many cases, is good but needs to be tweaked a little bit, and then it gets published. But of course, there are always stories of papers that have crazy ideas that did get through. And I should back up here and say physicists, being physicists, have a tendency to go their own way a little bit. We, in the early 1990s, mid-1990s, started this thing called the Archive, ARXIV, which is now housed at Cornell University, which is a preprint. And basically you dump papers there before they've been published. But it's all untested theories, unpublished and stuff like that. There are many physicists and many famous papers that never leave the preprint. Like it never gets fully published for whatever reason. It just never gets fully published. I have a paper on there that has been cited by papers in Nature, but that I just never submitted for publication anywhere for various reasons. Actually, COVID was the main reason for that. But it's got citations to it.
Okay, so why do we need journals if a journal and peer review can't actually provide a stamp of authority that says that the paper is actually correct?
The thing about it is that to get promoted or to get tenure, if you're in the US or Canada or someplace like that has tenure, or if you have in another country that has something equivalent to tenure, you often need to show publications in peer-reviewed journals. And so there's this rush in these cases to get ideas out there. And I think there's also a rush, especially in some applied areas, to get your ideas out there, because if there's any chance of spinning off the technology or turning it into something practical, you want to lay claim to it.
I just want to ask about the review process. And this isn't to pick on this particular journal or what happened in this particular case, because I think this is standard practice. There wasn't that something particularly went wrong here. You know, people might have the sense that if it has appeared in a peer-reviewed journal, then it's been checked thoroughly and it must be correct.
No, it isn't what happens. And I review a lot of papers and I try to replicate the math, but some of it's very, very complicated. And at some point you look at things and you kind of, it looks 99% right. I think I'm going to just say, this looks like these guys did their homework. Let's pass them. I want to emphasize, I'm sure I'm going to get blowback on this, but everyone does that. That doesn't mean we don't thoroughly read through papers. It's that sometimes arguments are so abstract, the math is so deep, that it's hard to completely be 100% sure that it's right. And I'll give you an example. There was a mathematical proof about 25 years ago or 20 years ago. The proof was something like, it was like 100 pages. Very unusually, the journal published a letter along with the proof that said, our reviewers have gone through this. They are fairly certain it is correct, but it's so complicated, they can't be 100% sure that absolutely everything was true. It got published, and then the authors launched a project, I think it was called the FlySpec project, to actually prove that the proof was true. So if you read the details of what happened, say, in the University of Rochester case, it's not a case of, oh, this guy just published this graph that he literally just made up, right? There is this debate about, well, did you subtract out the noise? And if you subtracted out the noise, how did you subtract out the noise? And there are multiple ways to subtract out the noise. Did you do it the right way, or did you do it the way that everybody agreed? And does your data still stand up to scrutiny there? And it's not straightforward. So just because a paper has been published doesn't guarantee that it's 100% absolutely right. All that peer review means is that it passes muster as making a valid argument. And I think a lot of people miss that fact.
So at the very least, we can pat ourselves on the back. We did have a little conversation before we started recording and quickly went back and checked last year's top 5 to make sure we hadn't actually picked out this particular result that got retracted, and we didn't, so well done to us.
Yeah.
Had it been correct, it would have been, a groundbreaking result, and it did get a lot of attention for that reason. But I guess it's worth always just bearing in mind that the process of publishing is perhaps a little bit more complicated than we just kind of assume. So with that bit of sort of tidying up done, let's go on, hopefully, to more positive things. We're still not quite on the list.
No.
What subsection of the not list are we currently on now?
We're in the newsworthy subsection, so I can't necessarily say the next one is positive. I just want to briefly mention that this year there seemed to be a big inflection point, particularly in physics and math and computer science circles and engineering circles with the release of GPT-4. And actually, I would say even academic circles in general, because everybody's freaking out about their students using ChatGPT, which is based on GPT-4 or could be based on GPT-4, depending on which version you buy. So GPT-4, it was released in the spring. It led to a huge public outcry. There were 2 famous letters that were published, open letters, one calling for a pause on this research and one that was calling for additional work to be done on consciousness in order to better understand this research. I will disclose the fact that I was a signatory to both. It, of course, has led to a lot of hand-wringing in a lot of circles, and it does seem to be a fairly big inflection point and has led to some very detailed discussions about what these AI models are doing. Specifically, GPT-4 is a large language model, an LLM. And so there's an idea of trying to understand what an LLM really is doing. Is it actually reasoning or not? And there's been a long debate, and it's gotten testy at times.
I don't want to dwell on this one because it's a little bit out of
No.
our sort of subject area. But when we say there's something to be concerned about or people are getting freaked out, there are different levels that you can get freaked out at. What are you referring to here?
So at the level, say, of a high school or college English teacher, they're maybe freaked out because students could go in and have ChatGPT write their paper for them. But that's not the point. I think the bigger point is, at what point do these things become a danger to humanity? What are the consequences of having these large language models? And also there, DALL-E, which is a visual AI that can create art. What kind of danger to humanity do these things pose? I just read an interesting blog post by FQxI member Scott Aronson about this. He's a bit on the freaked out side, which is interesting since he consults for OpenAI, which actually makes ChatGPT. So I'll just say we're living in interesting times.
We'll put a link to Scott Aronson's blog post on the podcast page, qspace.fqxi.org. Scott there talks about how a decade or so ago he dismissed the notion that AI could become a realistic threat anytime soon, but now he has started to change his mind and he gives some reasons. At the same time, it is very important to emphasize that there has been a lot of criticism, also from some very distinguished AI experts, of the dangers of overstating the AI doom scenario, which is perhaps smaller and a much more speculative risk, many say negligible. And the worry is that the focus on these ultra-pessimistic, more sci-fi notions of humanity's destruction at the hands of AI distracts attention from some current and very real-world harms of AI today on people's lives. Ian, you mentioned AI creating pictures, often trained on the art of humans without their permission or knowledge. And AI, we know, may be replacing and displacing workers. There's been, lots of talk about that. And there have been very long-standing concerns about AI amplifying discrimination and bias based on the data it has been trained on.
I don't think we're anywhere near the realm of, the robots are going to take over and humanity is doomed. But I think it raises ethical questions. Are they conscious? Personally, I don't think they are at the moment, but a lot of respectable people do, or think they are at least at the level of where they're actually doing reasoning. And it raises concerns about not just about what the AIs could do, but what nefarious people in the world could use the AIs to do. The reason I brought this up as part of our podcast is because it is a foundational question, because a lot of the people in FQxI are thinking about these issues of consciousness and intelligence and agency, and we've been doing it for years. Those questions are sort of directly applicable to this issue right now. It just felt like a big inflection point. We had a campus-wide meeting, emergency meeting called as a result, and a lot of colleges and universities did the same thing. It's something to keep an eye on.
Well, GPT Etc had to be mentioned, and so we've done so, and it's something we can keep an eye on, assuming we're even still here next year and we haven't been killed by AI or by something else, which hopefully will provide you with a nice segue to your next talking point, Ian.
All right, so the next one crosses this boundary between newsworthy and being a runner-up. A number of years ago, I made a big deal about the climate crisis, and I got some pushback on that, saying that there's no real reason to bring that into this kind of a podcast, et cetera, et cetera. But I said, well, it's a dire situation. We should keep a finger on the pulse of things. The newsworthy thing that is not necessarily foundational, but interesting, is that at the recent COP28 meeting, the world leaders have, in theory, pledged to phase out fossil fuels by, 2030 or 2040 or something like that.
Yeah, not quite that optimistic, 2050, I think, but at least that's something.
Related to that, though, there was an interesting discovery this year related to weather in general, and it actually involves quantum. There was some work done this year by some physicists that were able to explain some of the oscillating weather patterns of Earth's atmosphere by treating Earth quantum mechanically as a topological insulator.
A topological insulator is a material whose interior behaves as an electrical insulator, whilst electricity can be conducted on its surface due to quantum effects.
Now, that doesn't mean that Earth and Earth's atmosphere actually is a quantum state of matter. It's not. But the idea was that they were able to use this method of treating it as a topological insulator to explain some of the large-scale weather patterns that we see on Earth's surface.
The weather patterns are so-called Kelvin waves in both the air and oceans that can be around 1,000 kilometers long and for oscillating weather patterns such as El Nino. So geophysicists had a mathematical description for Kelvin waves, but it wasn't perfect. Now, Brad Marston at Brown University and others have found similarities between the flow of fluids in these waves and the motion of electrons in topological insulators. So the question I have for you, Ian, is this just an analogy? Is this something where they are using the same mathematical equations in two situations? How far does this similarity go?
So a topological insulator basically is a material where the interior is an insulator, but the surface is a conductor. Electrons can only move along the surface of this material. It's an insulator for the same reason that a regular insulator is, which is, again, a quantum mechanical reason. We don't think about this when we teach introductory electrical circuits or something. You don't have to know that it's a quantum phenomenon, but it is a quantum phenomenon, and it has to do with there's an energy gap between what are called the valence and conduction bands of the atoms. And in order for an electron to actually conduct, it actually has to get bumped up into the conduction band. But in a topological insulator, the bands are twisted around relative to a regular insulator. It's that twisting idea that I think is what they were using as a way of modeling some of the twisting that goes on in the weather patterns and the flow of the atmosphere on the surface of the Earth. I don't know if that made any sense.
No, it didn't at all. And I'm laughing because goodness knows whenever I have to write about topological insulators, it just gives everybody a headache, especially me, also the editors. And usually if I ask any two researchers who work on the topic, one of them will give me an explanation that I like, and then I'll present it to the other one and they'll be like, no, that's not how it works at all. It's something completely different, and come up with something even more complicated. And that seems to be what has happened here. We've got something which I think people might be able to visualize more easily, which is the weather being described in terms of some weird quantum matter that not very many people do understand. But you haven't answered my question, and that was, is this just an analogy? Or is this something where they've actually used the equations or whatever the theory that they use to understand topological insulators and applied it directly to understanding weather patterns?
My understanding is that it's a little bit of both. So it's the equations, but it's more than just the equations. Particularly, this is related to Earth's equatorial waves. So there's a flow of air around the equator that is very interesting and very complex, very turbulent, and it's very hard to model it. The flowing of the actual waves in Earth's atmosphere, they behave a little bit like the swirling interior electrons inside these topological insulators. It's not that Earth is actually a giant quantum object per se, but it's that not just the equations match, but that there's actually this sort of physical thing that looks very much like what's actually happening inside these topological insulators.
All right, I've got a bit of a cheeky question now. Last year, this time, we spent a lot of time talking about whether wormholes had literally been produced in an experiment in the lab. And in the course of that discussion, we got into talking about a conjectured correspondence between quantum equations and gravitational equations, called the ADS-CFT correspondence, if you want that jargon. Is this another example of a correspondence principle?
Correspondence. It's a little bit like ADS-CFT in that the math seems to work. And that although in ADS-CFT, the two roots to the math, they were discovered via different routes. Here, it's somebody took something from quantum mechanics and said, who knows what it means, but let's just see if this math actually models what's going on. And it does. It seems to work. But it doesn't necessarily mean that the Earth is this giant quantum state of matter, because I'm fairly certain it's not.
Well, if it was, that would have been number one. So we have reached the end of our newsworthy items, which moulded into our runners-up with the last item there. Links to more about each of them will be available on the podcast page, qspace.fqxi.org/podcast. In the next episode, a few more runners up, and then we shall start the countdown proper. In the meantime, you can find us on Twitter/X, Facebook, Instagram, TikTok, YouTube, some other stuff, Mastodon, Blue Sky. Search for FQxI or FQxI Physics. Thank you for listening. Thank you to Ian Durham. I've been Zia Morale.